Yesterday we spent some time looking at velocity time graphs, the shapes of velocity time graphs, and comparing them to position time graphs. But in addition to that, finding things, specific things from the graph, such as the velocity at a specific moment in time, or the acceleration, or the displacement. Today, I want to do an example, and then we're going to look at a couple of questions on a worksheet to illustrate the concept that we're looking at here now. So here's your example. This is on your worksheet. If you want to flip in your worksheet booklet to, I think it's the 4th or 5th worksheet. You're going to velocity time graph. Hey, tell me what's the manipulated variable in this graph? Emily, what's the manipulated variable? Time. And how do you know that time is, Emily's right. How do you know, Kessler, that time is the manipulated variable? How do you know that Emily is right there? Yeah, it's on the x-axis of the graph. We don't know details of this experiment, but we do know from the graph that time is on the x-axis, and the manipulated variable is always on the x-axis of this graph. Now you can see that the responding variable is on the y-axis, and you can see that the title is consistent with that. It's always responding versus manipulated, or y-axis versus x-axis. If you had a data table here, which of these two variables would appear in the first column of the data table? Would it be velocity or time? Nick? That would be time. Good. The manipulated variable, the first column of the data table, the x-axis of the graph, always go together. All right. We want to find the velocity of the object at 4 seconds here. What are we going to do for finding the velocity at 4 seconds? Good. We're going to go up and over. Go up and over, and it looks like it's going to be 15 meters per second to the east. We'll define east as positive, so we don't have to write the word east in every single time we answer one of these questions. Good. Calculate the change in velocity over the entire graph. Now, it's kind of hard to tell exactly where some of the points are because the graph isn't great. There should be more grid lines to make it easier to see, right? I promise you on a quiz or a test, there will be more grid lines, so it will be easier to see where the lines are intersecting. But roughly, what's the change in velocity of the entire graph? How would we do that? Shay, how are we going to find the change in velocity over that graph? Okay. Cool. Yeah. Good. It's up and over times 2 and then subtract. So in other words, we're finding the velocity just like we did in question number 1, but we're doing it twice, and then we're subtracting. So we're going to go up and over at 10 seconds. Looks like it's 33 seconds. Sorry, 33 meters per second, minus the initial velocity, which is, looks like 3. So we're going to say the change in velocity there over the entire graph is 30 meters per second. Shay, does that make sense? Okay. The acceleration of the object over the entire graph. Remember, there's a couple of options for acceleration. One of them is what? Mallory? Careful there. Okay, I think you're thinking the right thing. You're not quite saying it right, though. She said velocity over time. Nick, how can we improve on what you just said? Okay, you say slope, yeah. Slope, absolutely. Yep. Change in velocity over time. That's important, right? Because we can't just take any velocity and divide it by time. We have to take the change in velocity divided by time. So I don't care whether you go delta y over delta x, rise over run for the slope, or whether you go delta v over delta t, you're going to get exactly the same thing. I'm going to choose to do delta v over delta t because I have delta v already. I just figured it out in question number 2. 30 meters per second divided by the time interval of 10 seconds gives me an acceleration of 3.0 meters per second squared. So number 2 tells us how much it's speeding up by. Number 3 tells us not how much it's speeding up by at all. Number 3 tells us how quickly it's speeding up, the rate at which it speeds up. And 4, the displacement of the object over the entire graph. This is the hardest part right here. How do you find the displacement on a velocity time graph? On a position time graph, it's easy, right? Up and over, subtract the 2. But Holly, on a displacement time graph, it's going to be, yeah, the area. Be careful how we say it here. We don't want to necessarily say the area under the line, because if you happen to have a line that's below the x-axis, it's actually the area above the line, right? The area between the line and the x-axis. In this case, it happens to be below the line. So let's look at this. We got a crazy shape here. So what we're going to do is break that up into two sections here, a rectangle and a triangle. Now again, the grid lines aren't, there's not as many grid lines as there should be, so it's kind of hard to tell where each of these lines starts and ends, but we'll do our best here. Let's call this one first block and this one the second block. Let's say A1. It's a rectangle, and the equation for a rectangle is length times width or base times height. The base here is 10 seconds, and the height here looks to be 3 meters per second. Now, take a look at the units here. Sometimes I get a little lazy and don't write in units, but I specifically wrote them in here because I want you to see something. Typically, we'd say area is meters squared, right? But when you're multiplying seconds by meters per second, which is what we're doing here for base times height, what happens? Seconds on the top, seconds on the bottom cancels, and the units we end up with are meters, which is exactly what we should end up with, right? Because the area is the displacement, and displacement should be measured in meters. Area 2, this is a triangle. So we're going to say it's 1/2 base times height. 1/2, this time the base is still 10. And the height goes from 3 to 33. Go ahead. Yeah, it's 30. Yeah, sorry. That's a big one, boy. Should be 30 meters. Thank you. The height is 30. Be careful here, guys. Like some people, when they see this height, say, oh, 33, right? No, it's not. The height of the triangle goes from 3 to 33. So the height of the triangle is 30. Does that make sense? We're not going from the very base of this problem, from the x-axis. We're going from where the triangle starts, which is 3 meters above the x-axis. 1/2 of 10 is 5. 5 times 30 is 150. And we add those up, and we get a total of 180 meters. Now, if part of that was below the x-axis, we make it a negative value. We'd still add it up the same way, except we'd have to be careful to make something negative if it was below the x-axis. Right? Listen, I mentioned this yesterday. I don't think that this is crazy hard. Okay, position time graphs, certainly you guys did a really good job on position time graphs. You guys aced that quiz. I think you'll ace this quiz too once we're going to give you some work on it here today. Check over that work on Monday. Probably have a quiz on Tuesday on this stuff. I think you'll ace it. The trick is when we have a test where I give you a position time graph or a velocity time graph and it's out of context. So I say, here you go, here's a graph. And we've done both, keeping them straight, right? Knowing which one is which. And knowing that for a position time graph to find displacement, all you do is subtract positions. For a velocity time graph, you find the area and so on. Okay, we can do all those things, but when we start having the questions mixed up a little bit, sometimes you get a little bit confused as to which one is which. Okay, keep that straight, and you guys are going to be just fine. All right, we're going to finish off class here today with the rest of your worksheet, the 4 questions on the back of that page. And those are going to be homework if you don't finish them in class here today.